Hi, everyone, and welcome to this episode. Today we are studying for our chemistry final exam. And if you're here, it's likely you're taking a high school chemistry course, maybe in 10th grade, 11th grade, 12th grade, whatever it happens to be. And because it's June coming up soon, you'll likely have a final exam happening. And so we're going to make a series of videos reviewing the units that are typical of a high school chemistry class. And today we're starting with Unit 2, significant digits, accuracy, and precision. So a couple of words about the way I've numbered my units. These are the way I typically do them in a normal chemistry class. And at the beginning of the year, we're often kind of doing two units at once, what I like to think of as two units. We're learning about properties of matter, we're looking at states of matter, we're looking at chemical and physical changes, and all those things that we want to use to classify matter. But we're also starting chemical laboratories. And in the laboratory, you measure stuff a lot. And so we start to learn how to do good measurements and what do we do with the numbers that we get. And so I'm going to be kind of doing these both nearby each other, but separately, treating the math component and the chemical component a little bit differently. And the order of my units might change from the order of what you had in your class or what you teach, but that's okay. Just look for the title that you need, and it should be there. So we're going to do this one to kick us off on how to take a good measurement. What are significant digits? You've probably heard of those. How to report the number of sig digs in a measurement. How to carry sig digs through your calculation. Rounding your answers at the end. Accuracy and precision. How to maximize your accuracy and precision for future chem labs. And what to do with percent error. So let's get into it. I wanted to start with a quick little example. All right, so let's pretend you're in the chem lab or anywhere, and you have a ruler and you're trying to measure this object right here represented by this rectangle. And take a moment and pause and take a look at this picture and see what you think the correct measurement should be. All right, and if you did that, congratulations, that's extra nerdy. So I'm looking at this object, and I can see that it's definitely over 8, and you always want to check the unit that you're measuring in. What's your instrument giving you? Is it grams, liters, milliliters? This is centimeters. And so I can see that it's definitely above 8 and not to 9, okay? So I should definitely put an 8 as part of my measurement, because I can see that it's at least 8. But I can also see that it's a little bit more than 8, right? It's not just right on the 8, it's actually up here. So I start counting 1, 2, 3, 4, 5, 6, 7. I can see that I've hit the 7, and I'm actually a little over the 7. So I'm going to put the 8 there because I know that. I also know there's a 7. Okay, and is that the best I can do? That's the big question today. And I'm going to argue that it's not the best we can do. Because if you look really carefully, there's the line that I'm measuring actually kind of goes between the markings. Can you see that? And because it's going between the markings, that gives me a tidbit of information that is a little bit better than saying 8.7, because I can clearly say it's not 8.7, but 8.7 something. Now, do I know that something exactly? Maybe not. I have to estimate it a little bit. And so I'm going to estimate maybe an 8.73. I don't think it's to the halfway point of that space in there. But that digit right there means something because it tells the reader that it's definitely a little bit more than 8.7 and approximately 8.73. Now, I know that might bother you. Oh, you got to put a unit. Numbers in chemistry class without units, they're evil and we don't like them unless they're pH values or equilibrium constants, but that's another story. All right, so how to take a good measurement. Here's the definition. When you're taking a measurement, you're going to have an instrument with some information on it. A good measurement shows all digits given by your instrument plus one more, and that's the biggie, which is an estimate. Even if it's right on the line, report that extra digit. A lot of people cut themselves short and they don't give themselves enough information. They're like, oh, it's about 8.0 or it's just about 8 or something like that. Whereas in this case, 8.73 gives the maximum amount of info. I don't want to go 8.729430 because that's implying a lot more accuracy than I actually have. And I don't want to lie to you or anybody. And so even if it was right on the line, like what if it was 8.7 or maybe like this, right, 9.1, and it was right on the line? Well, you always want to look at your instrument and say, what place is my instrument giving me to? and then add one more. So if this is giving me definitely to the tenths, I need to go to the hundreds. Even if it's right on the line, give that hundreds and let's call it 9.10 centimeters, because we estimated to the hundreds and our instrument gave us to the tenths. So always go one more, which is an estimate. Unless you're using like a digital scale or something, they just give you whatever digits that the scale knows, and you can just write those down. You don't have to estimate beyond what the digital scale is giving you. An analog scale, you might want to do the estimation. Okay, so just report those numbers. All right, so you've probably heard the term sig digs, and maybe they're still a mystery, maybe they're not. Hopefully they're not, but here you go. What are sig digs? When you properly record a measurement, those digits actually convey meaning about the magnitude of the measurement. They're not simply numbers anymore. They are significant. They're important, like your significant other is important to you, because they tell us something about the sample being measured. This is why they're called significant digits. They mean something. They are now attached to the object you were measuring. That object has that measurement, and it's significant and it's important. So we get really excited about significant digits in chemistry class. Maybe you've come around and gotten really excited about them as well. Okay, so when we do significant digits, and you write down a number, some of those digits are actually going to be significant and some of them are not. And this might seem arbitrary, but just go with me on it. First of all, any non-zero digit that you write down is significant because you measured it and it's a non-zero digit. It's a 4, it's a 6, whatever it is. Zeros between two non-zero digits are also significant. So if you had a measurement like 2.04 centimeters, that O is pretty important because it tells you that it's not up to the 1 yet and it's still down at the 0. Trailing zeros are significant, like in my 9.10 measurement a minute ago. That 0 is important because it shows that you measured it. Leading zeros, though, are not significant because they only tell us the measurement hasn't started yet. Start counting at the first non-zero digit. So like if we have a measurement that's really tiny, like 0.00039 grams, those first zeros, they're not that important because they're just telling us that the thing is tiny and we haven't gotten to the measurement yet. So don't count those. And also, if you ever have here's the difference between measured quantities, which is something you measure with a little bit of maybe a little error, a little estimation, contain only as many sig digs as were actually measured. Defined quantities, however, contain an infinite number of sig digs because they are defined to be exactly some number. Like 1 meter is 100 centimeters, but also 1.00000 meters is 100.0000 centimeters. It's defined and it's exact. So you would not limit your answer to that number of sig digs in your rounding. So in order to deal with significant digits correctly, we have to first be able to identify how many significant digits are in an actual measurement to begin with. And so that's what we're starting with here. So you might see a question like this: how many significant digits are in these measurements? Might be a multiple choice question, might be open-ended, or you might just be doing your lab data and you have to deal with it. So first things first, let's do a couple and then I'll have you try a couple. All right, in part A, I can see that all 4 of the digits are non-zero digits. Now, it should be noted, I'm assuming that these are properly recorded measurements, that somebody read the instrument and estimated one more digit and then stopped without giving too much accuracy. So, okay, so that's 4 digits of significance in that very first example. And in the second example, we see that there is a middle zero. So 12.076. So that's going to be important because it tells me that it was 12.0, but not quite to the 1. So we continued with the 7.6. So I'm going to count all 5 of them as significant. Now, a trailing zero is also significant because it means that somebody measured that. Somebody said, yeah, it's 3.3, and I should go one more place, and it's right on the line. So it's important. So we're going to keep it. However, these leading zeros are not going to be considered significant. And I know some of you are probably like, well, they're important too because they're holding the place. They're like, it's a completely different number if you take them out. Well, that's true, but they're just telling me that the measurement hasn't started yet. And if I put this into scientific notation, 8.42 times 10 to the minus 4th, they disappear, but I still have the same exact number. So they are not as important as the other one. So I'm going to start counting here. 842, that's 3 sig digs. So you take a moment, pause the video, and try the last 2 and see if you can guess how many significant digits are in those. And if you did that and came up with 5 and 1, congratulations, that's excellent. This trailing zero is significant, so all 5 are important. But in this tiny example of a tiny amount of meters, is 0.000003. We start counting there, and there's only one digit. So that's all the accuracy that we know about. And those do not count as being significant. Okay, they're placeholders, but they're not significant to the measurement. So that's part 1. And before we talk about the 2 rules for using sig digs in a calculation, let's just do a calculation. Okay, let's imagine for a moment 3 different students measuring 3 different objects, and they want to get the total mass of all 3 objects. So the first student comes up with this mass using a nice sensitive balance, 24.837. The second student, 3.02, and the third student has an object, 1.1 grams. That's all the instrument gave to him, and that's what we got. So we add them all up, and up until chemistry class, most people would just grab their calculator, start hammering away on it, and they get this 28.957 and write it down, move on, and not even think about it. However, okay, this is where we have a problem. So when you add up numbers, you go by decimal place, 7, and there's a number here, but it's not shown. And so I don't really know what it is. So while this number carries down in the bottom as a 7, it might be a 7, but I don't know for sure that it is going to be a 7 because I don't know what the thousandths place is here, and I don't know the thousandths place is here. They might both be zeros. Great. But they're probably not zeros. So that means this 7 is uncertain, and I don't know it. So you know what? I'm not going to report that in my final answer because I just don't know it. On the other hand, we got a 3, a 2, that adds up to a 5. But again, there's this digit that I don't know. This might be a 5 if I knew what that digit was, if that was a 0, but it's probably not a 5. 9 times out of 10, it's probably not going to be a 5. And so it's uncertain, and I don't know it. The only number I really know for sure is the decimal place that they all have. 8 and 1 do add up to a 9. And I know that because that's a 0. And so my answer should be reported with this, and this, only to the tenths place, not any further, because all the measurements have the tenths place, and not all measurements have the hundredths or the thousandths place. So the rule for that is when you're adding and subtracting, you round your answer to the decimal place of the least accurate measurement, the one with the least accurate decimal place. You're going to the decimal place, and that's the tenths place in this case. But I do want to round it because I have 957. I already know there's a 57, which is over halfway. It might be more than that, and it probably is more than that. So I am going to round this up. 28.9 becomes 29.0, which would probably be the best answer that I can put. And some of you are like, probably, why are you leaving digits there when you have so many that you can give? But we only want to report what we know and not imply that we know more than we actually do know, because that is lying, and we don't like lying in chemistry. All right, now it's your turn to try to do one of these. Take a moment, add up these 3 numbers, and round them to the correct decimal place. All right, and if you did that, and again rounded it to the tenths place, then congratulations, I came up with 20.0. My actual initial answer is 19.963, but again, because I don't know the thousandths place or the hundredths place, I only know the tenths place in all my measurements. So 19.9, but again, it's a 6, so I rounded it up to 20.0 grams on that. Let's take another look before we look at the second rule. So let's say we're finding a density of some kind of metal, and we find that our sample has a mass of 57.248 grams, that's 5 digits of accuracy, and 12.3 milliliters, which is 3 digits of accuracy. And I punch it in my calculator. Here, this grams divided by mils. My calculator gives me this, and that's a lot of numbers. And a lot of us would, before chemistry class, just dutifully write them down, because my calculator gave them to me, they must be correct. But there's a better way. And here's what we have to think about. We have to think about the number of digits of accuracy in our original numbers. Not decimal places, but the number of digits of accuracy. This one has 5 digits of information. This one has 3 digits of information. And when you take a 5 divided by a 3, there's no way you're going to get 10 decimal places of good information if your original numbers only have 5 and 3. So we have to chop it down. And where do we chop it down? We chop it down to the number of digits that the least accurate measurement has. So the one with the fewest digits. So this one has 3, this one has 5. Because this is lower, I'm going to keep this one, and this one, and I'm going to chop it off after that third digit. So my best answer is 4.65 grams per milliliter. And I'm going to get rid of those because they might, in theory, be correct, but I don't know them, so I'm not going to report them. So that's your best answer. So the rule for this one is when multiplying and dividing measurements, round your answer to the number of significant digits in your measurement with the fewest number of sig digs. So that's the rule. Take a moment, write it down if you want to. And let's try one more. Here we're multiplying. We do a lab in chemistry class where we find the area of a piece of metal foil in the process of finding its thickness. I made a video on that if you're interested and you have done that lab. The metal foil has a length of 14.2 centimeters and 23.94 centimeters. Somebody didn't read to the correct number of decimal places up here, but that's what we got, 3 and 4 digits. So count them, 4. Length times width, so you're going to multiply them together. Your calculator is going to give you 339.948. That's too many digits. So what are we going to do? We need to chop it off at 3 digits. So 3, 3, 9. We're going to chop it off there. But because this is a 9, let's round it up. And we ended up with 340 centimeters. And that's really all that I can honestly say with any amount of certainty that area is. And you might be thinking, well, I don't have any decimal places. It's not good. And well, it's as good as we can get. And that's what we do. All right, let's change gears for a moment and talk about the difference between accuracy and precision. I ask my students this all the time just to start things up. And a lot of students say things like, well, accuracy is getting the right answer. Precision is like really getting the right answer, which is a common misconception. It's actually not true. Accuracy, yes, is how close you are to the accepted or true value. How close you are, that's accurate. But precision is something completely different. It's how close your values are to each other. And that's a measure of consistency rather than accuracy. For example, I used to play golf on the golf team when I was younger. I still like to play golf when I can. But I can tell you that I very rarely hit the ball straight. Like, I've tried to hit the ball perfectly straight every single time, and it never does. But, so in terms of accuracy, my ball is off center a little bit every single time. And so I'm not as accurate as I'd like to be. On the other hand, I am pretty precise because when I usually hit my normal shot, I play a little bit of a fade and it goes a little bit to the right. And it's fairly predictable. And so my shots, if I take 20 shots from the same spot with the same club, they usually go to the same place. And so that's precision. It might not be as accurate as I wanted it to be, but at least I can count on that precision. So that's an example of that not in the chem lab. But here's a picture with some data on it. If we imagine that the accepted value is the bullseye, trying to get to it. If we have a wide range of values, they're not going to be accurate, and a wide range of values is going to be not precise either. It's possible, though, to be like my golf swing, my golf shots being precise, but a little right of center and not as accurate as I'd like them to be, but at least their precision is decent. Here we have a wide range of values, but if we average them, we would get an answer that's pretty close to being accurate, but the precision's not there. But to be accurate and precise is to do both and get them close to the true answer and repeatedly close to the true answer. Here's a little dartboard analogy. You might have seen something like this. Accuracy and precision both good. Here it's precision with no accuracy and just bad accuracy and bad precision, and you can decide for yourself which dart player you are. Okay, so how do we deal with this? We're getting close to being done with this episode. How do we maximize accuracy and precision? You might see questions about this after you've done a bunch of chem labs and have this experience. Since every measurement might involve a little bit of error, because there's always an estimate there, we look for ways to minimize error. So one way to do that is to use a larger sample size. And what that does is, let's say your instrument is good to the 10th place, and you're measuring a tiny sample, and you're off by a 10th. That might be a significant fraction of your sample. But if you use a bigger sample, but you're off by a 10th, it's a smaller fraction of your sample, so you have a less error. So bigger samples typically mean less error. Use a more sensitive measuring device. So if you have a choice between a scale that goes to the hundreds and a scale that goes to the thousands or the 10,000s, use more digits because that'll give you more accuracy. Use a higher concentration of solution. I see this question a lot on AP chemistry exams. How could the student have found the enthalpy change to a better degree of accuracy? And one of the ways to do it is to use a higher concentration of solution. So you get double the reaction or triple the reaction, triple the temperature change, and now you've got a wider temperature change. So if you're off by a little bit, you can have a little bit less error. And also, it's very important to use the same instrument for multiple measurements. So if I'm in a laboratory with several scales or balances, I want to pick one and I want to use the same one every single time, because if each one of them is calibrated slightly differently, I'm going to be off by a random amount each time. But if I pick the same one and maybe it's measuring too low by a tenth of a gram every single time, well, at least all my measurements will be down by that and it'll be much more consistent. So just a little theory for you there. And sometimes we need to report our error. So let's do that. Error, as the word suggests, is what was your error? How far away from the correct value were you? In a lot of cases, we do know what the correct value is, the accepted value for something. And that might be a molar mass from the periodic table or a density or something like that. And we use the term accepted because, for example, the density of iron is 7.86. Is that it? Like, does it? Well, in theory, the exact density of iron goes all the way out to 1,000,000 decimal places. We just don't know them because nobody's been able to consistently measure them beyond the first 3 or maybe 4 digits. But we all agree on those first 3 or 4 digits, and so we say the scientific community has accepted them, and so we call it the accepted value. So your error is the accepted value minus your value. Just find the difference. And I put absolute value signs in here because sometimes you'll get a negative answer if your value is bigger than the accepted value, and that's okay. Just drop the negative. We're just going for how close you are. Okay, so let's look at 2 examples. Let's say student 1 has an accepted value they're gunning for at 2 grams. They're supposed to get 2 grams of stuff, and they got 1 gram of stuff. So their error is 1 gram, right? A different student was supposed to get 1,000 grams of something and got 999 grams of something, and their error is also 1 gram. So they did an equally good job, didn't they? Well, you're probably like, no, they didn't do a good job. This guy lost half of his stuff, and this person got almost all of it, was just off by a tiny bit. But their actual magnitude of error is the same. So what do we do with that? How do we give them a little bit more credit for doing a better job? Well, what we can do is do a percent error. And there's a formula for this. You're going to want to know this formula because you don't want to be asking your teacher every single time you do a lab, how do I do a percent error? Because they'll get really annoyed at you, speaking from experience. And so example 1, the accepted value minus your value, that's the error, but divided into the accepted value again to get a percent times 100. And so the first person was off by 1 out of 2, that's a 50% error. But the second person was off by 1 out of 1,000, which is 0.1% error. So a much better percent error down here than up there. It relates it to the size that you're supposed to get. So let's do 1 or 2 quick examples, and we will be done with this episode. Example 1, a student finds the density of aluminum to be 3.1 grams per milliliter, and later finds the accepted value to be 2.7. What is the percent error? So the way you do this is setting it up in your lab notebook. Always a good idea to write the formula that you're using. So percent error, and then we would do the absolute value of 2.7, which is the accepted value, minus 3.1, which is what they got. In this case, units are not as important, but over 2.7, sorry about that, times 100. And if you tap your calculator, you're going to get a negative 14.8, or drop the negative and you get 14.8%. So this number is 14.8% off of the original accepted value. And our last pause the video moment for the day. Take a moment, pause the video, and see if you can find the percent error for this example. The density of copper is 8.96. If a student finds the density of copper to be 7.42, what's the percent error? All right. And if you ended up with a percent error of 17.2, then good job. We are on our way to mastering sig digs and errors. And again, my calculator gave me more digits than that, but because I only had 3 digits in all my answers at the beginning, I'm only going to use 3 digits in my final answer. All right, so there you have it. A quick little rundown of sig digs and taking measurements in the chem lab. Here's our list of topics again. If you have any questions for me, send them in the comments or directly. In the meantime, happy studying and have a great day.